Welcome back. We are going to stop computing things explicitly for the moment, and instead we're going to ask whether things are finite or infinite. That is more or less what we're going to be concerned with. What things? Improper integrals. Okay, so I'm going to actually spend the whole time on improper integrals, but I may not even finish. In fact, I probably won't, so next time. Chalk malfunction. Okay, here we go. What is an improper integral? Well, let's write down this integral. If f is continuous, for example, on the closed interval a to b, then it can only get so high or so low. It can't just keep going up and up like have an asymptote. That would be a discontinuity. So I want to distinguish between a nice bounded function f that's trapped between two horizontal lines and ones which are sort of unbounded. They stretch vertically. So the prototypical sort of thing I'm considering, say this is AB, there might be something like a vertical asymptote at A. So if we want to find that integral in this circumstance, what we're really looking for is this area. But that is not the actual area because this goes up and up and up and so on. It never stops. So it's a region that's not bounded itself. The region sort of has this infinite extent. So this area, how much paint would you need? Well, of course, you can never actually do it. And perhaps that area is infinite. But sometimes a sort of mathematical miracle occurs, and this thing is somehow close enough, the curve and the asymptote are somehow close enough that the area is finite in some sense. So my first goal will be a little theoretical. I'd like to spend I'll probably end up being 45 minutes on the theory, and that's chapter 20 of my book. Then the rest of the time is going to be focused on how to solve problems involving improper integrals, and there are a whole lot of techniques that you need to be aware of. And this, I feel, is a topic I haven't seen a very thorough presentation in books, really. I mean, I've seen some decent, but not really in-depth. So I'm going to go quite in-depth. This is really maybe the topic that inspired me to write the book and start these review sessions, all that sort of stuff. Okay, so in any case, that's one sort of issue that can happen. Of course, the asymptote could be on the right, or it could be in the middle, or there could be more than one. So that's one type of problem. Soon we'll see another type of problem that makes an integral improper, where one of these bounds is infinity or minus infinity, or maybe both are infinite. And so that's a sort of separate case. Let's start off with this. How are we going to define what it means to take this area? Well, let's suppose that we don't get too ambitious. Instead of starting at A, we'll start a little bit to the right of A, say A plus epsilon, where epsilon is a positive number that's pretty small. I mean, I certainly don't want to bust out to the right of B. I need to stay in here. But so if I only content myself with this area, there's no problem because there's no blow-up. There's no vertical asymptote. Everything is nice. This blue, there is some area. Then I say, okay, so what is that area? Well, the blue area is the integral from A plus epsilon up to B. Then I say, okay, but I actually want all the white area, so I redraw A plus epsilon, say, over here. So now I take the new blue area. And I keep pushing this over and over and over. I can never actually make it equal to A because the function blows up, but I can make it very, very close to A. So I'm actually going to take a limit as epsilon goes to 0 from above. I don't want to allow negative epsilon because then I'd be out here. So I'm going from the right down and I am trying to take these integrals, and I'm going to say that if f is a function whose only blow-up, a blow-up is basically a vertical asymptote as far as we're concerned. Just as an aside, there is another, well, there are other types of blow-ups. I mean, you could have one of these funky oscillating things that goes like this and up and, I mean, that is not a vertical asymptote, but an integral, integrating this function, you'd still have to do the same trick. Luckily, in this course, we're not going to worry about these crazy functions very much. Most of the time, basically all the time, they're just going to be asymptotes, vertical asymptotes. Going to be the problems that we're dealing with. So if there is a vertical asymptote at x equals a, and no other blow-ups in between, then this is going to be equal to this by definition. That's what this means if a is a blow-up, and the only blow-up in the whole closed interval. If a is the only blow-up, we define it equal to this limit. But you know, sometimes limits don't exist. So if the limit exists, if it exists, in that case we say that the improper integral converges. And I will often write this as CVG, converges. So this integral has a problem at a, because it blows up. So we have to use a limit to define it. And remember, the integral sort of has a limit in it as well, so it's almost like a limit of a limit. But luckily, the integral notation kind of includes the limit in it. You don't have to worry about that one. You've only got this one. So if it exists, we say it converges. If this limit does not exist, if not, or it's infinity, or minus infinity, then we say that the integral diverges. And I'll often just write div for that. So those are the possibilities. So the improper integral, a lot of the time, the limit here is infinity. And so this integral is infinite. In the context of this picture, the only thing the limit could be, because these blue areas are getting bigger and bigger as you slide this vertical line to the left, the limit could be infinity. That's the only way in that particular picture that this limit wouldn't exist. So that would mean you need an infinite amount of paint. Even if you had all the time in the world, you would need an infinite amount of paint to cover this. So you might be wondering, how could anything converge? How could anything converge at all? Well, let's just look at two particular integrals, just to get a perspective on this. Suppose we look at the integral from 0 to 1 of 1 over x dx. And I'm also going to look at the integral from 0 to 1, 1 over root x dx. Okay, both these functions, if you graph them between 0 and 1, they look pretty similar. They both look something like this. They have a vertical asymptote at 0. They go through 1, 1, and they keep on going. So we're sort of looking for this area, but remember, it goes on forever. Well, let's deal with this. This is the only problem spot at 0. This is the only blow-up point. Everything else is nice. So the way to deal with this, by definition, because this is a problem, we have to take a limit as epsilon goes to 0 from above of just epsilon to 1. Right? If epsilon were equal to 0, this would be from 0 to 1. Instead, it's just close to 0. And we can do this. Forget the limit for the moment. Let's just do the integral. 1 over x, the integral is natural log of absolute value of x between epsilon and 1. So what is this? This is, again, the limit as epsilon goes to 0 from above of log 1 minus log of epsilon. We don't need the absolute values because 1 and epsilon are both positive. Well, log 1 is 0, so this is just the limit of negative log of epsilon. Well, what is log of 0? What doesn't exist, but what's log of a tiny, tiny positive number? It's pretty close to negative infinity. Remember, here's a little sketch of log. So log of epsilon is a huge negative number. Minus log of epsilon is a huge positive number. The limit is infinity. So if this graph is y equals 1 over x, which it more or less could be, I mean, I didn't do a very good job of the asymptote over here, but it has one. If this is y equals 1 over x, that area is infinite. What does this mean? It means this diverges. Because we did not get a nice finite number. By the way, I tend to think of diverges as bad and converges as good. I mean, I'm not trying to say infinity is bad. It's just when you get it, you normally say, I don't know what's going on. Whereas if it's finite, you feel like you could whip out a can of paint and start painting the thing and not run out. Okay, well, integral of 1 over x diverges. How about the other one? Well, again, there's a blow up at 0. So we have to resort to this limiting definition. So we integrate from epsilon to 1. And, well, an antiderivative, 1 over 2 root x, the antiderivative is root x. So this time you get 2 root x. Yeah, just differentiate that and make sure you get this. We're going to go between epsilon and 1. So this is 2 root 1 minus 2 root epsilon. As epsilon goes to 0, the square root of epsilon goes to 0. Actually, it's lucky we're going to 0 from above so that we're not taking the square root of a negative number. So this is indeed 0 in the limit, and the answer is just 2. Well, that means this converges. Not only does it converge, it actually converges to 2. So the interpretation is that if this picture over here is actually y equals 1 over root x, of course I'm not claiming it's the same function, but this would be a semi-decent graph of y equals 1 over root x, then this area, even though it's infinite in extent, it goes up, the actual area is 2. Which would mean that if 1 can of paint painted 1 square unit, you would never need more than 2 cans. You never actually finish because you'd be going up forever. And you'd get very close to running out of the second can. You'd have mere drops left, but you'd never need more than 2 cans. In fact, you'd use up as much as you like of that second can. A question? Well, you know, this is going back to Math 103, really. I mean, square root x is a continuous function. So if you can just substitute, well, square root of epsilon is a continuous function of epsilon. So I more or less just plug in epsilon equals 0 and see if it works. Right? The first thing you try with the limit is just plug in the value and see if it makes sense. It's only if you have, normally if you have something where you're dividing by 0 or something like that, or a logarithm, such as in the first example, that you have to be careful. Another question.
And what was the relationship between that graph right there and 1 over root x?
Okay, so the question is, what is the relationship between this graph and the integral? So this is supposedly a picture of, say, y equals 1 over x, right? And so this integral from 0 to 1 should be the area under the curve down to the x-axis between the vertical lines x equals 0 and x equals 1. The problem is that this thing doesn't actually meet. Normally, you sort of got a nice box or a weird curvy sort of thing. Here, it just goes up and up and up forever. I mean, I can't really draw it, but imagine going to the ceiling and this curve still doesn't hit this line. Now go up to the moon. They still haven't hit. They're really, really close. Now just go further and further, and this never actually gets there. And I'm asking you to paint this with an ever thinner little bit of paint that just goes up. But it's never a line. It's always got some width. Okay, so apparently, well, if you do it for that function, you keep on needing more paint. You have to just keep buying paint. It's a bit of a pain because you've got to go all the way up to the moon, then back down to the hardware store and buy some more paint, take it back up. Okay, well, that's sort of silly. But the fact is that if this instead was a graph of 1 over root x, which looks very similar, then somehow you only need 2 cans of paint at 1 square unit per can to do it. And what's going on is, if you actually draw them on the same set of axes, 1 over x is just somehow a little bit bigger than 1 over root x. And even though they both have an asymptote, this white curve, y equals 1 over root x, is closer. It sort of hugs it closer than 1 over x does. And it's sort of, as I say, it's a bit of a miracle, but somehow it converges. Somehow it's finite. So that's the whole game of this. Now, in this particular example over here, we know what it converges to. The answer was 2. That is very unusual. As far as we're concerned in this topic, almost every question is going to just be, does it converge or does it diverge? If it converges, you might want to know to what. Most of the time, you can't easily work it out. You might get a rough idea, but you may not get an exact answer. Okay, so this is very different from most of the stuff that we've done so far. Most of the stuff, the answer has been, what is the value of blah? And you need a number. Here, it's just a yes-no thing. Converges or diverges. So it should be easier, right? Well, no, because you've got to give reasoning. You've got to prove something. Every improper integral question, more or less, you have to prove something. So here are some computations. Most of the time, we're not even going to be doing computations, but I'm getting a little ahead of myself. More on that in a second. Anyway, so here is an example of an improper integral that diverges. Here was one that converges. So you see, there is some interest in it. Just because there's a vertical asymptote, we don't know which one it is. We need to investigate. Now, before I go on to the other type of improper integral, what if the asymptote is at b instead? So you're trying to find this same integral, but you have a vertical asymptote at b. Well, not a big deal. If the asymptote is at b, and there's no other asymptotes, then we'll define the improper integral. You just go from a up to b minus epsilon. So you sort of make your cutoff here. And you find that blue area. And then you push this over. So b minus epsilon, you still want epsilon to go to 0 from above. And you just chop it at the right. So there's nothing to this. It's just the backwards version of the other one. But conceptually identical. All right. How about if it's in the middle? Do I want to do this yet? Yes. How about if it's in the middle? Actually, I do want to say one other thing first. Take a look at this integral. Integral from 0 to 0.001, 1 over x. Does that diverge or converge? Well, we could repeat the previous computation, but the truth of the matter is we don't have to. This right-hand endpoint doesn't matter. Everything is to do with 0. That's where the problem is. This is the thing that's causing this to diverge. Now, we know it diverges when you go all the way up to 1. So what does that mean? Well, if you draw a picture it looks like this. 0 to 1, we know we need infinitely much paint to cover all of this going up. So what if instead of going up to 1, you only go up to 0.001 instead? Well, you need infinitely much paint to go all the way up. You only need finitely much paint to go this part. It might be a lot of paint, but you only need a finite amount. This, although it looks small, this is where the infinite is in this case. So this extra bit, no matter how much of the interval from 0 to 1 it is, it doesn't affect the convergence. The same thing is true if you take 1 over root x, where that, in that case, it does converge. Again, this now, the whole thing would be finite, and you take away a finite thing from a finite thing, and it's still finite. So the point is that if you know that this integral converges, and you adjust b, suppose that the problem spot, the vertical asymptote, is here at a. You can change b, it doesn't matter. If the original integral converged, then the new one will, and if the original integral diverged, the new one will diverge as well. The only exception is if you change b and increase it so much that you pick up another asymptote or something like that. That could be bad. That could be bad. So, you don't want to push b over to infinity, or if the function happens to do this at 2 and you push b all the way up to 2, well, then you'll pick up a new problem or a new blow-up point. So b doesn't matter within reason. You don't want to pick up any new asymptotes. Okay? So that's an important point. It's only really the behavior very, very close to the asymptote that matters. So, of course, you could change this number to any finite number, a positive number, 0.00001, or 11, or a billion, and that integral would still diverge. But if you change the 0, well, suppose we change the 0 and we go from, say, 0.0003 up to 1. Well, that converges because there's no problem spots. It doesn't include 0. There's no vertical asymptote at 0.00003 up to 1. This could be very high. In fact, it is very, very high. But it doesn't matter. We've still got a finite area. The region itself is bounded, and therefore this converges. It's only when the region itself just cannot be enclosed and keeps on going that you even have an issue. It's very conceptual so far. We've seen a couple of examples. I need to just do a little more of concepts and then start giving you some tools that will help, because doing the sort of computations I've just been doing is sort of not always feasible. Are there any questions? Shout it out if you have one. Okay, so now I'm going to tell you what to do if there's an asymptote in the middle. Well, suppose we're going from A to B again, and there's some asymptote at a point C in between A and B. Well, the idea here is that you have to split the integral from A to B. You want to consider this as the integral from A to C. So you just go up to the left, worry about this part, and then worry about the right part. So that second integral is this part. Okay, well, we can deal with both of them. I'm not going to write it out, but this one, you would go actually c minus epsilon and take a limit, and this one you go c plus epsilon and take a limit as epsilon goes to 0. So you have two improper integrals to worry about. Now, what do you think happens if they both converge? You need a finite amount of paint to do this part and a finite amount of paint to do that part. Well, to do the whole lot, you can deal with a finite amount of paint. So if both of these pieces converge, then so does the whole thing. But if either piece diverges, so does the whole thing. If you need infinitely much paint to do this half, it doesn't matter if you only need finite to do this part. That's no consolation. You still need an infinite amount of paint. So if either one of these diverges, so does the whole thing, i.e. the left-hand side. If both pieces converge, so does the whole thing, the left-hand side. So the implication when you're actually doing a problem is if you have split up an improper integral into two pieces, and you look at them one at a time, and you find that the first one diverges, don't even bother looking at what happens with the second one, because you know then the whole thing diverges. So, on the other hand, if it converges, you have to check the other piece, and hopefully that converges as well. If that second piece diverges, it invalidates the whole thing. So divergence, one piece divergence, whole thing diverges. Every piece converges, so does the whole thing. Now, I say every piece, there's only two pieces there. Sometimes you have to split an integral up into multiple pieces. So, for example, consider, let me just look at what I would like you to consider. Okay, consider this. Integral from 0 to 3, 1 over x, x minus 1, x plus 1, x minus 2 dx. Consider that. If you wanted to investigate this, and I'm not going to do it until probably next week, I'll have to come back and do it, but just to sort of get you on the idea of the splitting, where we've got asymptotes at 0, 1, -1, and 2. Now, the -1 doesn't matter because it's not between 0 and 3. So the blow-up points between 0 and 3 are at x equals 0, x equals 1, and x equals 2. Those are the only relevant blow-up points. So if you want to understand this integral, let's see what's going on here. We've got 0, 1, 2, and we're going up to 3. We've got a vertical asymptote here, vertical asymptote there, vertical asymptote, and then no problem at 3 itself. So the function might be doing something like this. I don't know, maybe it's negative for part of it. I'm not doing much of a good effort to find out, but this is like hypothetically the issue. I don't really care about sketching it. What I care about is splitting up the integral so that each piece only has one blow-up, only one vertical asymptote. So I don't even want to go from 0 to 1, because then I'll have one at 0 and one at 1, and I can't deal with two problems in an integral. It's bad enough when you have one problem. So just pick any number between 0 and 1. It doesn't matter. You could pick your favorite number between 0 and 1. I might as well just pick a half, but you could pick any number between 0 and 1. And then I'm just going to go from 0 up to a half. So the first integral will be from 0 to a half of the same quantity. And now this integral only has a problem spot at 0. That's the only blow-up. It's the only thing that causes us any grief. The next integral will be from a half to 1 of the same thing. I'm not going to bother writing it out again. That is, of course, going to have the problem at 1. That's where the blow-up is. And then we'll have another integral from 1 up to, well, we don't want to go all the way up to 2 because then we'd have a problem at 1 and at 2. So we'll go up to 3/2. And again, it's the same integrand. And then we need to go from 3/2 up to 2. And that will take us to this asymptote. And then we can go all the way from 2 to 3. There's no blow-up. Same integrand, dx. I'm trying to save myself the trouble of rewriting that integrand. I'll come to the question in a second. I just want to identify the problem spots for each integral. You see, I've split it up into 5 pieces. The original integral up here, this integral equals these 5 pieces, the sum of the 5 pieces. And if any one of those pieces diverges, so does the whole thing. Now, it turns out they all diverge, but as I say, I'm not going to do that till next time. A question?
What if this function was all positive, but it still has so many asymptotes?
It doesn't matter the positivity of or the negativity.
Why not just take the integral from 0 to 3, and if you get infinity or infinity, then you know that one of them diverges. Why took so many times?
The question is, why not go from 0 to 3? And don't worry about the stuff in the middle. I'll give you a quick example. Suppose that you take the function y equals 1 over x squared. Okay? That looks like this. And suppose you want to go from -1 up to 1. Okay? Well, let's suppose we ignore the problem spot at 0, right? That you agree there's a problem at 0. What I've just said, we should split up this integral here. We should split that up into 2 pieces, from -1 to 0 and from 0 to 1. Suppose we don't, and we just try to work it out. Okay, what do you get? Well, an antiderivative of 1 over x squared turns out to be -1 over x. Right? Differentiate 1 over x and you get negative 1 over x squared. So negative there will get rid of the negative here. And we go from -1 up to 1. And if you plug this in, you get -1 over 1 minus -1 over -1. So this is 1 minus 1, which is -2. Okay? So if this computation is valid, this area is -2. And yet, the area is above the x-axis. There's no way it's -2. It's meaningless. It cannot be the right answer.
We know it diverges.
It doesn't diverge, though. Oh, yeah, no, it does actually diverge. Sorry, I take it back. It does diverge. But you don't know, no, you do not know that it diverges as a result. You have to split it up and integrate each piece. You cannot integrate across an asymptote using the fundamental theorem. This computation assumes that the fundamental theorem is true. And when we stated the fundamental theorem, we said that the function has to be continuous. Or perhaps it could be in piecewise continuous bits. You can make it more broad, but it does not allow for asymptotes in the middle. It just fails.
It won't give you the right area, but if it gives you a wrong answer, then you know that it diverges.
No, that's not necessarily true. I don't believe that that's true. I think that there are examples of divergent functions, of convergent functions, where it gives you something that's just whacked out anyway. Right? I can't think of anything off the top of my head. I might be wrong. But this is, what you're proposing is not a legal, certainly not in Math 104, way of seeing that something like this converges. You just cannot just substitute and ignore this. You have to see what happens. You have to see what happens. I'm sure there's plenty of examples, actually, where it fails. But I'm not going to think of one off the top of my head. But I do want a good piece of chalk. The bad chalk, the evil chalk has reappeared. There's 2 types of chalk. Look at that. We get a close-up on this chalk. If anyone from Crayola is watching here, see this chalk that gets wider and gets narrower there? It sucks. I hate it. Do you know why? Because it doesn't erase. Make this one. I know you can do it. It's got your name on it. Maybe the other one you think is easier to hold. Well, I don't care. If it doesn't erase, I don't want it. All right. But I digress. Okay. So we've seen how to split up integrals. Now, I would like to show you the other type of improper integral. We've looked at improper integrals that involve vertical asymptotes. What if you have a horizontal asymptote? I'm talking about an integral that looks like this. Instead of a to b, I'm going to go up to infinity. So what could this mean? Well, suppose you have a function with a horizontal asymptote, let's say at 0. That will be what we really want. And we go from a, and we want to go all the way, not to the moon, but to the right. I know the Earth is round, so we'll eventually come back. But forget about that. Just go on forever. So this time we're painting and painting and painting and so on. Same issue. Same issue. Does it converge? Does it diverge? What does it even mean? Well, instead of using an epsilon, now what I'm going to do is cut it off at some point n and look at this area here. So that blue area is the integral from a to capital N f of x dx. And then I'm going to sort of say, okay, well, let's try again. Let's move n here. So we'll pick up some more area. And we'll keep shifting n to the right. We'll let it just get bigger and bigger. Each time we fix n, we get a valid area, assuming there's no problem spots. Of course, if there were vertical asymptotes as well, you would split up the integral first. But you move n to the right more and more and more. In fact, you want to push it to infinity. By definition, this integral equals this limit if it exists. If the limit exists. And in which case, of course, again, we say that this integral converges. If not, the original integral diverges. So it's very similar. It's very similar. In fact, we can take a function y equals 1 over x now looks like this. Suppose we go from 1 to infinity. So suppose we take the integral from 1 to infinity of 1 over x dx. Okay? Contrast this with the integral from 0 to 1, which we did before. Now, there's no problem at 1. The problem is up here at infinity. That's what's causing the problem. So we'll take the limit as n goes to infinity, integral from 1 to n of 1 over x. And you get log absolute value of x between 1 and n. So this is the limit as n goes to infinity, log of n minus log of 1. Log of 1 is 0. What happens to log of n as n gets large? Well, if you draw a graph of log again, it does go up to infinity. Here's n. As you shift n right, this does grudgingly, but it just keeps getting higher and higher without bound. So you get infinity. So our integral of 1 over x from 1 to infinity, that area up here, again, you need infinitely much paint. You need infinitely much paint to keep going. It's actually not that surprising. If we draw it like this, 1 over x is completely symmetrical with respect to the x-axis and the y-axis. We need infinitely much paint there. It stands to reason we need infinitely much there. So we shouldn't be surprised about this. On the other hand, now let's look at this integral. Integral from 1 to infinity of, let's consider 1 over x squared. Could be the same graph, that graph up there. So I'm going to go from 1 to n. And the integral of 1 over x squared is minus 1 over x. We're going from 1 to n. So this will be the limit as n goes to infinity. Minus 1 over n minus 1 over 1. Which is the limit as n goes to infinity of 1 minus 1 over n. Now look at this. As n gets large, 1 over n goes to 0. So this limit is 1. So that shows that this integral converges. And it converges to 1. If you draw the graph of y equals 1 over x squared, you only need 1 can of paint to go. You also need a lot of time and persistence, of course, to keep walking down that way forever, but you'll never use up your can of paint. You'll get down to the dregs. But, presuming you go long enough. But you only need that 1 can of paint that covers 1 square unit. Okay, so that one converges, the other one doesn't. The graphs look almost the same. Again, what's going on is that this is hugging the x-axis more closely. It's a much more amorous asymptote, as it were. It likes to get real close. The other one does as well. It's just a little more standoffish, you know? It's keeping its distance. Okay, I'll get there. Just don't rush me. Well, don't rush you. You need infinitely much paint to cover the distance between us. How could you? Okay. It may not be the first time in history that improper integrals and romance have been discussed together, but it's probably not very common. So, you now have an idea of how the other sort of improper integral looks. Of course, you could have both. What if you consider, for example, the integral from 0 to infinity of 1 over x dx? Well, that has two problems. There's a problem at 0 because of the vertical asymptote, and there's a problem at infinity because of the horizontal asymptote. Or actually, whenever you've got infinity, that's always a problem. That always makes an that always makes an integral improper. You cannot have an infinity in one of the bounds without it being improper. So this, of course, has two problems, 0 and infinity, all the way down there. So in order to deal with it, you have to split up. Split. What's your favorite number between 0 and infinity? 1? Ah, that's boring. Mine's 5. It doesn't matter, remember? It's only the action near the problem that matters. Now, I didn't do the 0 to 5. I did 0 to 1, but as I said, the 5, the 1, it doesn't matter. That diverged from 0 to 1, so it diverges from 0 to 5. And we just saw, similarly, going from 1 to infinity, the infinity is bad for 1 over x. We saw that on the previous board. So it doesn't matter if you start at 5. It still diverges. So actually, both pieces diverge. Therefore, this whole piece diverges. Both pieces. But even if only one of them did, that would be enough to make the whole thing diverge. Great. So, that's the first section. That's part one. The theory behind this whole thing. Now, the second thing I need to do is tell you, or give you a toolkit. It's going to have 4 tools in it. They don't look like screwdrivers or hammers. They are integral tests. They are tests for improper integrals. Almost every problem that we're going to do is going to use some combination of those tools. So the next thing I want to do is tell you about the tools. And then we'll talk about how to use the tools. So I need to spend some time on the tools. Integral tests. So the first test, and let me give you a reference for this, we've moved into section 20.3. The first test is called the comparison test. Now, you see, the improper integrals that we've done so far, the few of them, using these limits with the epsilons or the n's, in every case we could actually do the integral. We could do the integral in the sense that we could find an antiderivative and then plug it in and take a limit. But we're going to soon be dealing with functions that are so nasty that you can't do them, or you wouldn't want to do them. And the great news is you don't need to do them. The aim is to take a complicated function and somehow replace it by a simple function, or a simpler function. So here's sort of what I have in mind. Suppose that I have a fiendishly nasty function whose equation is a real pain, and who knows what it looks like. Blah, blah. And let's say that function is f. And it has an asymptote at a, the left endpoint. So what we're trying to find is we're trying to find the integral of f of x between a and b. We know that there's a problem at a, say, because there's x minus a in the denominator of this, or something like that. And what we want to do is just see if this converges or diverges. We don't care what it converges to, if it does in fact converge. We just want to know, does it converge or does it diverge? Can I paint this with finitely much paint? Well, suppose that perhaps you have another function that always sits below this, that also has an asymptote, but somehow the new function, which I'm going to call g, sits below it. Suppose that this blue integral, blue area, is infinite, in the sense that the integral of g diverges. What do you think happens with f? Diverges as well. If you need infinitely much paint for the blue, the white is bigger. What's bigger than infinity? Nothing. It's still infinite. So mathematically, this would look something like this. But that is infinite. So this equation says that the area under the white curve is greater than or equal to the area under the blue curve, which we're assuming to be infinite. This only makes sense if both the functions are positive. So forget about negative functions for the moment. All the functions we're going to consider within the comparison test and the next test, the limit comparison test, they're all going to be positive. So I'm just going to say positive functions. They don't go beneath the x-axis. Or at least not between a and b. They can do whatever they like outside a and b. It doesn't matter. We're only integrating from a to b. Okay, so if that's the case, here you have a quantity that is greater than or equal to something which we already know to be infinite. Therefore, it itself is infinite. So basically, the statement of the test, at least in this form, is if f of x is always bigger than or equal to g of x, and in fact everything is positive, or at least non-negative, on AB, well, maybe it doesn't need to be actually at the endpoints, on AB, this is what you have, and this is what you choose. And let's think of this as nasty. You have a nasty thing, and you choose something nicer. So if this is true, and the integral of G diverges, then this integral diverges too. Again, by way of understanding what's going on, diverges also. And that is the comparison test. That is the comparison test, or at least it's one half of the comparison test. So here's an example. Let's just consider the integral from 0 to 1 of 1 over x squared. Now, we did actually the integral from 1 to infinity. We found it converged. How about this? We could do this using the limit epsilon to 1 because you can find an antiderivative of x squared, 1 over x squared. But let's just use the comparison test. When x is between 0 and 1, 1 over x squared is actually bigger than 1 over x. Right? Try it for 1/2. If x is 1/2, 1 over a half is 2, but 1 over a quarter is 4. So 1 over x squared is sitting on top of 1 over x. So this means this integral is bigger than the integral of 1 over x dx. And again, this sort of inequality is only legitimate because these functions are positive. I just want to say that again. That justifies this test. There's actually a bit of mechanics going on here with limits. You see, you can't see them. That has a limit in it. That has a limit in it. We're comparing two limits, and so the inequality, you have to be a little careful, but it turns out that everything works. And I actually give a justification of it in 20.3 to some extent. In any case, we've seen this one is infinite. We've seen that diverges. So this diverges. We already knew. How did we know? Well, we did a computation there. You might as well say, why didn't we just repeat the computation? Well, this isn't particularly nasty, but this is nice. This could be a whole lot nastier, and this would still be nice. And then the argument would show, as we have done, that this diverges by the comparison test. So as I say, this is not the best example to use, and we'll do plenty of examples that are more complicated. I just wanted to give you an idea of what the logic looks like. And when I do another example, I'll write it up more formally. This is just an exploration of the test. Believe me, in the next, well, this week and the beginning of next week, we're going to be using this test a lot. All right? So, that's one half of the test. Before I show you the other half, I do have to make a word of caution. You've got to get this inequality the right way around. Suppose that you screw up and you get the direction the wrong way around. So what am I talking about? Well, if you have your nasty function f, looks like this, with the asymptote over here. Suppose that accidentally you've picked, where's my blue chalk? Suppose that you have picked your function g to be bigger. So here's g. And suppose you know that you need infinitely much paint to fill that part in there. What does that tell you about the white part underneath? Well, if we did the math, so suppose that instead of f being bigger than g as it was, suppose f of x is smaller than g of x, so that its integral, this is what we care about, that's what we want, is less than or equal to the integral of g, which is infinite, say. Well, what we want is less than or equal to infinity. So it's either less than infinity, converges, or it equals infinity, diverges. Yes, this staggering piece of math tells us that the integral either converges or diverges. Whoop-de-doo. What have we learned? Absolutely nothing. We already knew it either converged or diverged. That's the whole point of the problem. So I call this the whoop-de-doo case. But again, that is not a commonly used term. So when I say whoop-de-doo, I just mean the sort of frustrated, yay, we learnt nothing. Okay? You've got to get this the correct way around. You need f to be bigger than g if this integral of g diverges. Otherwise, you're not entitled to say anything. Okay? A number that's less than or equal to infinity, it could be anything. You know, nothing. On the other hand, the other version of the test does require that way around. Suppose instead that you thought your nasty function f, and it's just going to be the same picture actually, suppose you thought your nasty function f converged, and you did find a bigger function. I put that blue. Same picture. You found a bigger function g. Suppose now that this blue integral converges. So you need a finite amount of paint to cover, even considering that it goes up forever. Because this is less paint, it's a finite amount of paint. So if the blue is good, is finite, the white is smaller and still finite. By the way, you can see what goes wrong if f can be negative. There you need negative paint, of course, but, you know, this just could just drop. G could be positive, but f could just have a terrible discontinuity, just plummet down and be negative infinity. So that's sort of what you've got to avoid.
How can it be negative infinity if you know the t, you know the function, you know what f is? So how could f have an asymptote b?
How could it have an asymptote at b? Well, the question is, yeah, how could it have an asymptote? Well, even if it only has an asymptote at a, and it looks like this, then, and becomes negative, then even if this was a finite area of paint, this could be a negatively infinite area of paint. The blue is no longer even telling you anything about the white. Here it's trapping the white up in between this. The blue is close enough to the line for the thing to converge, and it's trapping this white to be even closer. It's a sandwich principle, actually, is what it is. It's a form of sandwich principle. A little bit more complicated than that because it doesn't necessarily converge to the same thing. But here is the conclusion. I'll write it out again. If f of x is less than or equal to g of x, and this is, again, the nasty one you want, and this is a nice one that you've concocted, and again, I'm assuming that everything is positive. So if f is less than or equal to g, and the integral of g converges, then, and what I would write is the integral of f, this is what we want, it's this time less than or equal to the integral of g, which is less than infinity. By assumption, this new integral that you came up with converges, so it's finite. And in that case, this is less than or equal to something which is less than infinity. It's not infinite. Therefore, this also converges. It does not converge to the same thing as g, as the integral of g. But they both converge. In fact, it converges to something less than or equal to the integral of g.
How could f diverge at
Well, I am not saying, okay, so the question is, what if it does get negative? And I will talk about the negative case. But here's what I have in mind. F can have a vertical asymptote down here, right? And it can be very far from the axis in such a way that this diverges to minus infinity. And then you could find this G that is up here that converges, and this area could be negative infinity, even if this area is finite. That's the sort of thing that can go wrong if F is allowed to be negative and G can be positive. They just have no bearing. If you did have this case, you'd actually want to find, forget that G, you'd want a G that was down here. So you'd need to look at that. But as I say, I will talk about the negative case. Back on this, if you think your function converges, your integral converges, find a bigger function that also converges, and then use the comparison test. Again, you've got to get it the right way around. If your new function G sits underneath F and is finite, well, you'll end up with F is bigger than G, and G is a finite number. So I'm going to tell you a number, which could be infinity, is bigger than or equal to 3. Is it finite or is it infinite? Well, it could be 10, could be a million, could be a trillion, could be infinite. Whoop-de-doo. Again, we have not learned anything. Question up the back. How can you tell? Well, that's why I am going to spend a whole lot of time on problems. Basically, the idea will be that we're going to deal with functions which are polynomials and trig functions and exponentials and logs, and we will learn some nice rules of thumb about what to use. So the whole idea will be, you start off with your nasty function, you get an idea of whether it converges or diverges. So you'll know which one to do. That can be difficult. Then you're going to pick a simpler function, which I will talk about pretty soon, and you're going to say, okay, let's compare with that. Okay, so how can you tell? Wait and see. Great, so that's the comparison test. Again, I'm showing you the test. I'm not doing a lot of examples yet. They will come very soon. But I have a couple more tests to show. If there are any other questions, you know the drill. Okay, so as I'm erasing it, I tell you that the next test that I'm going to look at is called the limit comparison test. And it actually follows from the comparison test, but it's really useful by itself. And again, when I do the problems, I will show you exactly how you can tell which one to use. Sometimes you have a choice, but... So let's talk about the limit comparison test. LCT. You can write out limit comparison test for your own reference. In order to motivate this test, let me define a new nice notation. I'm going to say that two functions, f and g, I'm going to have two functions, and I want to define a twiddle. This is called a tilde, of course. But I'm going to say f twiddle g, f of x twiddles g of x, as x goes to a, say, means what? I kind of want these two functions to be close to each other. I actually want them to be asymptotic to. The official name for this is asymptotic to. But I'll probably just end up saying twiddle most of the time. So you'll have to forgive my non-technical language. Asymptotic doesn't roll off the tongue, rather. So f of x, twiddle g of x. The main aim is they're somehow supposed to be close. So if two things are actually equal, suppose f equals g. What would the ratio f of x over g of x equal? If this actually equal, well, this ratio would be 1. But, of course, they're only close to each other relatively, so we need a limit. This means the same thing as this. These two things are just different ways of writing the same thing. But this is a really convenient way of writing it because, well, first of all, because of the limit comparison test, which we will soon see, but also there are certain manipulations you can do with these relations which make life nice. So in order to see what they are, let's just see if we can write down any asymptotic relations. Well, here's one. Sine x, tilde, twiddle x, asymptotic to x, as x goes to 0. Do you believe it? Let's check it. What this says is the limit as x goes to 0, just copy that, of 1 divided by the other. It actually doesn't matter which one. That needs to be 1. Is that true? Sure it is. Trig limits. So actually you need to know all your Math 103 limits, I'm afraid. Everything. Everything. Yeah, it's like that. Math just builds in itself. It does not really forgive a lot of the time. Holes, buildings can topple down as a result. So, the limit as x goes to 0 sine x over x is 1. This means sine x behaves like x. This is another thing I will sometimes say. Behaves like. When x is close to 0, these two things are almost the same. At least the ratio is very close to 1. Okay? Now, the beauty of this is you can take this and you can replace x by some other function of x as long as it goes to 0 still. So sine of, for example, x squared tildes x squared as x goes to 0. Or sine of root x tilde root x. But this time we'd better say x goes to 0 from above because you can't take the square root of a negative number. How about sine 1 over x? Well, that tilde's 1 over x. You've got to be a little careful here. Maybe as 1 over x goes to 0. You see, i.e., as x goes to infinity or minus infinity. So sine 1 over x behaves like 1 over x, but not as x goes to 0, as x goes to infinity, or as x goes to minus. So you've got to be a little careful when you substitute. You're also allowed to multiply these things together. For example, we also know tan of x is asymptotic to x as x goes to 0. Right? The limit of tan x over x is 1. So because these two relationships, this and this, both hold as x goes to 0, you can actually multiply them together. It's true that sine x, tan x, asymptotes to x squared as x goes to 0. Or you could take any one of these and take a power of it. Suppose you go back to the original one. It's true that sine cubed of x, not sine of x cubed necessarily, but you just cube that and cube that. Again, you can justify all this by limits. We're just taking, in this case, we're cubing the limit of sine x over x, and 1 cubed is 1. That's on the right-hand side. So you can multiply, you can divide these things, provided, of course, well, no, I mean, you can basically divide them. You can take powers of them. You can do substitutions. It's a really nice sort of notation for these computations. Here's what you can't do. Sine x asymptotic to x as x goes to 0. Subtract x from both sides. No. I don't know. That's bad. Okay. Why is it bad? Well, there's a whole bunch of reasons, but the main thing is nothing can be asymptotic to 0. Remember, something asymptotic means that their ratio goes to 1. If this was true, then the limit as x goes to 0 of sine x minus x over 0 would have to be 1. That's a meaningless nonsense. So since you wouldn't write that, don't write that. Okay? So the thing that we've done wrong here is you're not allowed to add and subtract things. You cannot add, most of the time, you can't add or subtract the tildes. Okay, I haven't said what they're useful for yet, and I'm getting there. I just need to show you one more example. Here's another sort of example of where this comes in useful. Suppose you take 3x cubed minus 5x squared plus 7. What happens when x becomes very large? The highest term dominates. This is asymptotic to 3x cubed as x goes to infinity. Indeed, if you take the limit of the ratio of these two things, you just take the polynomial and divide by its leading term, that's going to be 1. We've seen this a lot. That's going to be 1 minus 5 over 3x plus 7 over... All of this stuff is going to vanish in the limit. It probably deserves one more line of working, but I can't bend down that much. So you'll have to do it yourself. All right. Any questions about that? Yes? Question is, you want to know, is this true? And I presume you mean as x goes to 0? Well, let's see. That would mean, if that's true, that would mean the limit as x goes to 0, sine x over x squared would be 1. And I put the question mark there to say that I don't know what it is. Well, let's see what it actually is. I mean, I don't know if it is 1. Well, the way I would deal with this is to split this up into sine x over x and then a 1 over x. That limit is surely 1, but this limit doesn't even exist. If it's a right-hand limit, then that's infinite. If it's a left-hand limit, it's minus infinity, but it is sure as hell not 1. So this is not true. So it has to be very precise, the functions. I'm not saying that there's only one possible choice. For example, sine x is asymptotic to tan x, because they're both asymptotic to x. So sine x, x tan x, so yes, they're asymptotic to each other. So it's not a unique sort of thing. But on the other hand, not every pair of things are asymptotic. Okay? Good. Okay, well, having developed that notation, we've got to return back to improper integrals, of course, and let's see if we can get a picture of what's going on in order to develop the limit comparison test. So here goes. Suppose I have two functions that both have, so I have a nasty one again, f, and I'm somehow going to pluck out of the air a nicer one, g, but this time I actually don't care which one is bigger. The comparison test, it was important. Here I don't care as much. What I care is that f and g behave the same way, are asymptotically equivalent. In fact, assuming the problem spot is only at A, I want to assume also, so assume f and g only have a problem spot, PS I'll use for problem spot. Well, maybe I better write it out this first time. Problem spot PS. Assume that the only problem spot in AB is at x equals A, the left-hand endpoint. And f of x behaves just like g of x as x goes to A. Say, from above is all you need in this case. So assume this is true, where, again, f is sort of the nasty thing you start with and the one that you want, and g is a clever function that you've picked out that's nice and you can really deal with. Well, what do you think happens? See, remember, in this picture, it doesn't matter what happens away from A. All the action is going on right near A anyway, so these wobbles are irrelevant. These two things are very close to each other as you get near A, in the sense that their ratio is close to 1. Right? That's what the tilde, the twiddly thing means. So suppose that this integral the integral of g converged. What do you think happens to the integral of f, which is, after all, very close? F is sort of similar in a way to g, at least near where the action's going on. So what do you think happens to the one that you actually want? If this one converges, it converges as well. On the other hand, what if that diverges? Then that diverges as well. They do the same thing. Then this and this both converge or both diverge. So practically speaking, i.e., this does the same thing as the simpler integral. And when I say does the same thing, I mean as far as convergence or divergence is concerned. Once again, if they both converge, they don't converge to the same number. It's just a qualitative sort of thing. They both converge to a finite number. You don't know what that is. You just have an answer to your question. So, let me give you an example. This is called the limit comparison test, as I said. So, e.g., suppose that, and here's our first really significant example. First of many. Suppose I take this integral. This is the first significant integral that you have to do, or let me say that again. This is the first real significant one that we've looked at in a way, because I don't expect that you know what the antiderivative of this is. Right? If you actually just had to find the indefinite integral, you'd kind of be screwed. I don't know what it is. Maybe you can do it, but it's pretty nasty. No substitution, that seems nice. I don't know how to do it. So the question is, though, not to find this, but to see whether it converges or diverges. So first of all, where are the problem spots? Well, sine x could be 0. It could also be negative. That would be a problem. But between 0 and 1, sine x looks like this. Right? By the time you get up to pi, which is close to 3, it's gone back down again. But between 0 and 1, sine x is positive, except at 0. You can take the square root. In fact, the only problem is when you divide by 0. So 0 is going to be a vertical asymptote. It's a problem spot. But otherwise, no problem. So the graph of this thing looks something like this. Same shape as a lot of the others that we've looked at. So, since we can't use the epsilon stuff, let's use the limit comparison test. I'm going to start off with the observation that sine x tilde x as x goes to 0. Remember, I said you can take powers of both sides of this, and it's still true. So I want to take the square root, which is the half power. This means that sine x square root asymptotic to square root of x. I just took the square root of both sides. The only thing you have to be careful of is you really need x goes to 0 from above. Otherwise, you can't take the square root. So that's true. Actually, I can now also take reciprocals. Maybe I should have done that in one go, just taken the minus a half power. Now, of course, you could start with this and you could check it directly by dividing this by this. I don't propose to do this more than once, but let me just show you why this is true in this specific case. If you take the limit of this top quantity here, actually, let's do this 1 over this. What the hell, it doesn't matter. I take 1 over root x and I divide by 1 over root sine x. I can manipulate this, get rid of the 1 overs, pull the square root around the whole thing, and you get the limit as x goes to 0, square root of sine x over x. Well, sine x over x goes to 1, so this goes to square root 1, but that's still 1. So this over this has limit 1. So as I say, I don't propose to do this for every example. Instead, you just take powers of these things and everything is fine. So, instead of saying this equals anything, I write this, the word consider. Very nice mathematical word, that. Consider the integral, well, let's write it as 1 over root x dx. There's an integral we've already done. We did it earlier. We know this converges. Also, from that working over there, 1 over root sine x tilde 1 over root x as x goes to 0 from above. So, we get for free, as it were, that that converges as well by the limit comparison test. It is important that you write limit comparison test, or LCT, to indicate what test you're using. Just as if you use the comparison test, you need to say that as well. That is so different from any of the computations we've done before. It's just completely different. It's a proof. It doesn't even have a single equals in the whole thing. Maybe if you go to this level of detail, it has a few equals there, but otherwise it's all tildes and a test, and it's just very different stylistically from the sort of problems we've been doing. Okay? So that's why this can be kind of off-putting. It's not just a computation. You have to make an argument. And it's really beautiful. We know nothing about this integral. We can't do it. We can't find an antiderivative. And yet, we know that we need a finite amount of paint, because that one worked. That one, we could find an antiderivative. All right, so that limit comparison test is what you use if you have the tildes. And again, I'm going to start fairly soon summarizing all the sort of tilde notation. I do want to say verbally, at least, as opposed to saying non-verbally, luckily, I want to just say to you a few little wrinkles or permutations. First of all, it also works if the problem spot is an infinity. Exactly the same way, instead of as x goes to a, you replace it by x goes to infinity. No problem. Another little wrinkle is that the new function g that you pick, in this case we started off with 1 over root sine x, and we got 1 over root x. The new function that you pick should not have any other problem spots. You don't want to introduce a new problem spot, which I call a spurious problem spot. That's kind of annoying. You know, you've got this problem spot, you're trying to analyze it, and you pick up a function that should be simpler, and there it is, and it's somewhere over here, it has another problem spot. So I will talk about how to avoid that when we do some specific problems. The only other thing that I want to say about the limit comparison test is notice that I have a function tilde a function. I do not have an integral tilde an integral. You are not allowed to write integral tilde integral just for two definite integrals. I'm not writing that down, but write it down if you like. I mean, basically, the integrals are numbers. Numbers don't twiddle. Functions twiddle. They get nice and cozy. Numbers are just numbers. Does 1.2 tilde, does that behave like 1.1? Not really. I mean, 1.2 is 1.2 and 1.1 is 1.1, and there's the gulf between them of 0.1. There's no asymptotics there. So do not write integral asymptote integral. Write function asymptote function, and understand that it means the limit of the ratio is 1. Okay, so that's all I have to say about the limit comparison test. Anyone have any questions on it? The question is, why did I draw the graph of y equals sine x? I was just trying to look at this integral here and decide where my problems lie. And my problems are going to be when this thing is either undefined or 0 in the denominator. And so I just wanted to convince myself between 0 and 1 that, first of all, I could take a square root because sine x is positive. And also that the only time that I get an asymptote is at 0. See, if I went all the way up to pi, so if this said 0 to pi, I would actually have a problem spot at pi as well, because sine of pi is 0. So I'd have to split it up and consider them separately. Also, if it went past pi, I would be really screwed, because then I'd be taking sine of a negative number, and the thing wouldn't even make sense. It wouldn't even be a question of convergence. There'd just be a whole part of this where the function isn't even defined. So how do you take an area under a curve that isn't even there? That is not a problem for math. That's a problem for philosophy. If we have any philosophers present, you might think about what it means to take an area under a curve that isn't there. Is the area there? If a curve falls on a graph and there's no one to see it, oh well. Okay, so now I can finally answer the question from the guy up the back, who is on his phone. Okay, whatever. That's cool. I can finally answer the question, which is, how do you know what function to use? And this is our third test, which is called the p-test. The p-test. And this is the source of functions that we're going to use for almost every problem. It looks like this. Suppose you want to integrate 1 over x to the p. Well, we've already seen a bunch of examples, right? We looked at 1 over x, that's p equals 1. 1 over x squared, that's p equals 2. What about 1 over root x? That's p is 1/2. So this thing could have a problem at x equals 0, or infinity, or both. But let's suppose that we just want to see what happens when we're going from a to infinity, where a is not 0. So a greater than 0, say. So does this converge or diverge? Well, it depends what p is. Remember, we saw that 1 over x squared converges. So this actually converges, in fact, if p is greater than 1. But we also saw that 1 over x itself diverged, and that turns out to be the barrier, the boundary. Diverges if p is less than or equal to 1. Now that's easily proved. We did it for p equals 2 and for p equals 1. It's not hard to do. It's in the book. And it's worth just checking out. There you need to use the epsilons, or in this case, capital N. You push n up. Take the limit as n goes to infinity from a to n of the same thing. So this is sort of bizarre in a way. But again, what it says is 1 over x looks like this. 1 over x squared is smaller. One over root x is bigger. And somehow, out of all this family of functions, 1 over x is the threshold. Anything smaller than that from amongst this family, such as 1 over x squared, or even 1 over x to the 1.0001, say from 1 to infinity, that converges because p is 1.0001. It's bigger than 1. And yet, if I take away this tiny little bit and make it exactly 1, it diverges. So in some sense, anything smaller than 1 over x converges. Anything bigger than it, or 1 over x, diverges. I want to emphasize that that is only true from amongst this family, as in 1 over x to the p. There are functions that are in between 1 over x and 1 over x to the 1.0001, or any other power. So you can actually go a little bit below that white curve here and still diverge. There's no last function that diverges before you hit converge. You can always just zoom in, and there's all this it's a mess. There's some magic line that no human knows. It's an unknowable line where if you cross it, you diverge on one side and converge on the other side. But you can't know it. You can't know it. You just have to look at individual cases. Or restrict yourself to a family like this. So that is the p-test at infinity. What happens at 0 is the reverse. You see, the orange curve 1 over x squared is now the bad one because it's too far away from the axis. Still has an asymptote. This is a very stylized diagram. You know, this is much, much closer. But now, the pink curve is the good one. The white one is still bad, and it's still the gatekeeper as far as this family is concerned. So, if you go from 0 to a, well, let's call it b, 1 over x to the p, this now converges if p is less than 1, and it diverges if p is greater than or equal to 1. So 1 is the bad one for both, but only just. Only just. And this, of course, is true if b is less than infinity. If b equals infinity, then you have to split up the integral. Actually, consider this. The integral from 0 to infinity of 1 over x to the p. Does that converge or does that diverge? Well, depends what p is, right? Well, not really. You split it up from, say, 0 to, now my favorite number is 6. Doesn't matter. And 6 to infinity. And it's a sad fact of life that if one of them converges, then the other one diverges. For example, if p is less than 1, this piece converges, but that piece diverges. If p is greater than 1, now this one diverges, that one converges. And if p equals 1, they both diverge. So in either case, there's at least one, or in any case, there's at least one of those two pieces diverges. So this actually diverges no matter what p is. It's kind of unfortunate. It's like a wobbly thing, right? You can wobble it, make it closer there, and that's good, but then it becomes further there. Or you can go the other way, but now it's too far over here. Or you can get something exactly balanced, but then neither of them work. It's a little sad. But that is how it is. Okay, so the point is, what's the point of the test? It gives you a family of functions where all you have to do is choose the p. And you can use these functions with either the comparison test or the limit comparison test. And these are nice functions because you know exactly what the answer is. There it is. It's part of the two things up there. That's exactly what the p-test is. It tells you which of these functions or converges depending on whether the problem spot's at 0 or infinity. So this is a beautiful, rich class of functions to choose as your g in either of the two tests we talked about before. Okay? Any questions? Okay, there's a fourth test. It's called the absolute convergence test. But I'm going to come back to that next time. I do talk about it in section 20, in chapter 20. I want to move on to chapter 21, which is now how to solve problems. How to solve problems. And we're just going to do about 25 minutes of it, and then next time I'll finish it off. Okay, so unfortunately I had to break it into two, but I knew I would. But this is now, I've given you all the sort of tools, theory, all that sort of stuff. Let's get practical. So, you are confronted by an integral that looks like this. I should have said the limit comparison test again. Everything has to be positive. I didn't say that. F and G have to be positive. Go back and write it in or something. There's a sort of prototype. Maybe B is infinity or something like that, or this is minus infinity. Who knows? F has a specific thing. What do you do when you have such a problem like this? Well, if F is negative, then you wait until next week or read ahead and see what to do, because I'm going to talk about that. So I want to just concentrate for the time being, for quite a while, actually, even the first hour next time. I want to look at what happens when F is positive. So let's just worry about F of x always greater than or equal to 0. Okay, so we're in this case. Well, the first thing you have to do is you have to identify the problem spots. So first, identify the problem spots, which I'm calling PS. So how do you know what's a problem spot? Well, basically, any vertical asymptote in A, B, and of course this can include A and B. In fact, a lot of the time it is at either or both of the endpoints, A and B. Also, infinity and minus infinity are always problem spots. I didn't talk too much about minus infinity, but it's basically the same as infinity. Instead of n, you do minus n. So that's how you find the problem spots. And you split up the integral into pieces so that each piece has at most one problem spot. And those problem spots should be either here at the left or here, not in the middle. I don't want, if it's in the middle, remember, you have to split it up into two pieces, as you found out by my repeated assertions that that's what you had to do, whether or not you believe me. So I want you to split it up so that each piece has at most one problem spot. And remember, so then look at the pieces separately. If any piece diverges, stop. Stop. Whole thing diverges. If all pieces converge, so does the whole thing. And the only thing I have to add to this summary is something that I've already mentioned. If one piece or the whole thing has no problem spots at all, so there's no infinity and there's no asymptotes or blow-ups, then it automatically converges. If no problem spots, automatically converges. It's a finite area. There's no infinite bits jutting out. It's just a nice finite area. So no problem spots, automatically converges. So that's how you get started. And you were asking about up the front about the root sine x there. Remember you saying, why did I check that? That's what I was doing. I was identifying to see if 0 was my only problem spot. Otherwise, I would have had to split it up. So I was sort of getting ahead of myself there, but now you see the beginning of it. Okay, so having split it up into pieces, we now can assume that you're going to look at each piece separately, which means we can assume that your integral has only one problem spot, and it's either at A or B. And so now what I'd like to do is embark on a rather long project that I will not finish. I'll see how far I get and just continue next time. The project is to understand how the common functions that we deal with behave. So I want to start, as anyone should always do, at infinity. Aim for the stars. So I'd like to look at the behavior of common functions at infinity. As I said, I'm not going to finish this today, so see how far I get. So here's the scenario. Most of the time when I say behavior of functions at infinity, I'm thinking that I'm going to analyze integrals that look like this. With a few exceptions. That's sort of what I'm dealing with, where this is the problem spot. So bear with me as I do this. Later, I'm going to do problem spots at 0, and then after that, problem spots at some other point. But actually, if you can do 0, you can do any other finite number as well. Okay, so here's the program. Polynomials, trig functions, exponentials, logarithms. Those are our favorite 4 types of functions. I want to spend a little bit of time reminding you what we know about them and seeing how to solve these problems. Okay? So we're getting pretty practical here. Let's start with polynomials. Polys at infinity. So here is the principle. How do you deal with a polynomial when it's large? Well, if you have a polynomial, it behaves like its leading term as x goes to infinity, or minus infinity for that matter, where this is the leading term. I.e., what I'm saying is polynomials, in words, behave like highest degree term. As x goes to infinity. Okay, so guess which test this suggests? Which test are we going to be angling for? Well, it's going to be the limit comparison test because it involves a tilde, a twiddle. Okay, so if you see a polynomial at infinity, that's probably what you're interested in. So here is an example. And this is from section 21.3. All right. Let's look at the integral from 1 to... Actually, we'll go from... Yeah, okay, I'll do this one first. 1 to infinity dx over 2 plus 20 root x. Well, you could use the comparison test. Also, this is not a polynomial, strictly speaking. It is a polytype, but the same principle still applies. I'm going to say 2 plus 20 root x. I want to think of this as 2 plus 20x to the 1/2. So this is x to the 0 here. This is x to the half. This is the highest degree term. And I'm going to claim that this behaves like 20x to the 1/2 as x goes to infinity. Highest degree term dominates. It's worth proving, just to be sure, since the limit of this 2 plus 20x to the half over just the 20x to the half as x goes to infinity, we want this limit to be 1. Well, sure, it is. Look, it's the limit as x goes to infinity, 2 over 20 x to the half plus 1. And of course, that goes to 0 because the power is on the bottom, and this is just 1. So that limit is 1. So, again, I write, consider just the integral 20x to the half. And if you like, the 20 is just a constant. It doesn't matter, so you could pull it out. 1/20th dx over x to the half. Does that converge or diverge? It diverges by the p-test, right? The p-test at infinity says it only converges if the power is bigger than 1. Problem spot's at infinity, remember. So, this diverges by the p-test. It diverges by the p-test. And you might as well say p equals a half less than 1. But less than or equal to 1. That's the divergence condition. Since 1 over 20 x to the half tilde 1 over 2 plus 20 root x as x goes to infinity, the integral from 1 to infinity also diverges by the limit comparison test. And that's the working. So what's required is to produce another function that tildes this, justify it by writing down the limit or some argument, and then claim that the new function converges or diverges using the p-test, and finally that the original integral does the same thing, diverges in this case by the limit comparison test. That is a very, very common form of argument. We're just going to be using it over and over again. In fact, so many times that I'm not even going to really write it out. I'll just say limit comparison test with blah. If I ever do that to save time, it's understood that you should produce something that looks more like this in order to get full credit. Okay, so you're going to have to allow me. I want to do a lot of problems without just writing out the same framework. Consider this, then buy this, buy this. They all look very similar. A lot of them look very similar. So some of the time I'm going to be saving time. Now, another example. Any questions about that example? You can holler it out. So I'm going to do another example of a trig function. With a little bit of a trick in it. Okay, check out this one. Suppose you want to look at, what is it, x to the 5 plus 4x to the 4th plus 1. Okay, so it's just a polynomial on the bottom. Notice I don't even think about using partial fractions to try to find this out. Where are the problem spots? Where are the problem spots? 0, you plug that in, there's no asymptote. Denominator is 1. Actually, the denominator is never 0 when x is positive. It's always at least 1. So the only problem spot is at infinity. That's the problem spot. Okay, so I take a look at x to the 5 plus 4x to the 4th plus 1. I'm going to claim that that tildes x to the 5 as x goes to infinity. And just for yocks, I'll justify it. Since limit x goes to infinity, x to the 5 plus 4x to the 4 plus 1. You divide by x to the 5, and it's really obvious that this is going to work. You just get 1 plus 4 over x plus 1 over x to the 5, and clearly that's 1. But you see, notice how I start with the polynomial to make my life easier. You can now take this, and you're fully justified in just taking the reciprocal. As long as you say as x goes to infinity. So I'm going to say maybe we should use limit comparison test with the same integral, but replace this integrand with the simpler one, which it tildes. The integrand tildes this, so just change the integral to the simple one. And of course you would write out the whole argument. Only problem is, what are the problem spots here? There's 1 at infinity, of course, because that's always a problem spot, but also 0 is a problem spot. The original did not have a problem spot at 0. This, I'm afraid, my friends, is a spurious problem spot. We have introduced a problem that was really unnecessary. So you need to do one little trick first. Split up the integral. Even though it doesn't have more than one problem spot, the fact that you're going to use the limit comparison test means that the new integral will have more than one problem spot. So we're anticipating the trouble. The way I would do this problem, especially if I'd done this, is almost the same. So forget about that. First of all, split up. Now my favorite number is 2. So I'm going to go from 0 to 2. And then from 2 to infinity. Doesn't matter where you go, actually. 2, 3, 10, pi, whatever, as long as it's positive. Tell me about this. Does it converge or diverge? Forget tests, just look at it. What problem spots does it have? There's an integral. Has no vertical asymptotes. 0 to 2. Converges. Converges, no problem spots. No problem spots. So that doesn't make a difference. That piece converges. Actually, everything is now riding on this piece. Now, here I'm going to say, consider the integral from 2 to infinity of dx over x to the 5. And now, unlike our first feeble attempt, we've got the function right. It's just, this is the only problem spot. Infinity. So does it converge or diverge? That integral there. Converges. Why? P-test, because 5 is bigger than 1. So this converges by the p-test. 5 is bigger than 1. Therefore, this integral converges by the limit comparison test. And I'm saving a line or two. You should really rewrite the integral and write it out a bit more. But as I said, I'm going to start abbreviating my solutions a little bit. Okay, so the point is that this piece converges, therefore both pieces converge. So does the original integral. So the integral we want at the top left there converges. See, it's a little bit tricky. You have to split it up and use the limit comparison test. You could also, again, use the comparison test, but for this type of problem, it's much easier to use the limit comparison test. Okay, I want to do one more example of this type before finishing for today. I believe we have a few minutes, right? Good. So I'm going to make sure the tape doesn't run out. There are there's another example in section 21.3.1 that is worth looking at, but I don't really have time to do it. Instead, I will pick the hardest example I can think of. It's from 9 to infinity, the integral from 9 to infinity, 1 over root x to the 4th plus 8x cubed minus 9, that quantity square root minus x squared dx. And the question is, does that converge or diverge, as usual? Well, what is the highest degree of the bottom? What is the highest degree term? Might think it's x to the 4th, but then you've got to take the square root. So it's like x squared for this piece. But then you have to subtract away x squared. So what's left? Well, maybe x cubed, but it's, you know what? Whenever you have something that is that diabolical, there is a trick you have to do first. Can anyone guess what it is? Conjugate, yes. Multiply top and bottom by the conjugate. You said multiply top and bottom at the same time as he said conjugate. It all works out. So, I know that's what you're going to say anyway, but here goes. I just couldn't hear it. Let's multiply top and bottom by the conjugate. So in this case, it's root x to the 4th plus x cubed minus 9 plus x squared over same quantity. Okay, so on the bottom, you just get the difference of squares. You get this squared, which kills the square root, minus x to the 4th. So actually, if you work it out, on the bottom, you have just the quantity 8x cubed minus 9. But on the top, you have x to the 4th plus 8x cubed minus 9 plus x squared. So we haven't done any calculus. We haven't even used any tests. We've just rewritten the integral. We've just rewritten it. Now, the bottom behaves like what as x is large? X cubed. Again, the only problem spot I should have said is at infinity. 9 is big enough so that this quantity is bigger than this, because the 8x cubed is quite big. You can see it here. 8 times 9 cubed is so much bigger than 9, and when this gets even bigger, this is never going to be 0. So the problem spot is at infinity. The bottom behaves like 8x cubed, but we have to do a little bit more work to deal with the top. What do you think this behaves, the stuff inside the square root? When x is large, what's important? X to the 4th. So now take the square root, x squared. 2x squared, right? So this behaves like x squared, this behaves like x squared. If there's any justice in the whole world, in the world rather, the whole thing should behave like 2x squared. I'm going to claim that that behaves like 2x squared as x goes to infinity, and I'm going to prove it. I want you to compare it with the original situation where we did x squared minus x squared and we left with nothing. You can't have 0. Nothing behaves like 0. Well, that's a pretty stupid sentence. There is no function that behaves like 0 other than the 0 function. So in some sense, nothing does behave like 0, because 0 is nothing. But I am now just playing with words. So let's finish off the damn question. This is since, well, I take limit as x goes to infinity of the square root plus x squared, and I divide by 2x squared. In order to deal with this, I have two separate pieces. Now, the 2 doesn't really matter that much, but if I pull it into the square root, it becomes a 4. So it's x to the 4th plus 8x cubed plus 9 over 4x to the fourth, whereas the other piece is just 1/2. Because I am silly, thank you. It doesn't make a difference, of course, to the actual problem, but I might as well not write things which are not real. Now, when I take the limit, of course, this is actually going to be a quarter, and the others are going to go away. It deserves an extra step, but I'm running out of time. So when I take the limit, I should get the square root of a quarter plus the half that I had from here. And indeed, that's a half, and that's a half, and I get 1. Okay, I'm going to continue the problem over here. We're almost done with it, actually. So I only need this bottom board. That takes care of the numerator. We also should just claim that the denominator behaves like its largest term as x goes to infinity. And you should just prove that with a quick limit. But basically, if you know the numerator behaves like 2x squared, and the denominator behaves like 8x cubed, then you are fully justified in dividing those two things by each other and writing that the whole integral that you've ended up with, x to the fourth plus 8x cubed minus 9, plus x squared, divided by 8x cubed minus 9. We've seen that the top tildes 2x squared as x goes to infinity, and the bottom tildes 8x cubed. So the ratio, the thing we're integrating, behaves like this. And this, of course, equals 1 over 4x. So from this integral over here, we're going to say limit comparison, and I leave the details of writing it out to you, but you're going to use limit comparison with the same integral, 9 to infinity. The constant 4 is irrelevant, it pops out. And you just end up with 1 over x. And you have to justify it using that tilde stuff. So does that converge or diverge? Diverges by the p-test with p equals 1. Diverges by the p-test. And so the conclusion is that this diverges by the limit comparison test because it behaves like 1 over x with the factor of 4. As you see, the constant isn't very important because a constant times infinity is still infinity, or a constant times a finite number is still a finite number. Okay, so anyway, that's a hard example. Next time we're going to continue with trig functions, exponentials, logs at infinity, then do the whole thing at 0, and it's going to be a lot of fun. So, see you next week.